How's everybody doing?
Good. Okay.
A school.
Sorry about the delay. I was in another meeting, so I had to jump out of that real quick.
No worries.
It's okay.
Did y'all just get the update from Dr. Matkin?
Yeah.
It's not showing up in my emails. What did it say?
That the drop date has been moved to April 17th
Oh, for this class?
for all classes. Yeah.
Oh,
The
wow.
semester.
Yeah.
That's really far.
It really is. But you know, when I looked at some of the other colleges that are still having classes, they're about out there too. So I think it's only fair. That's for sure.
I missed that last part. He said, how long are we going to be out?
Well, no, the drop date has been moved from this Monday to April 17th.
Okay.
So if you know, for some reason you feel like you need to drop a course, you can.
Okay.
Up until the 17th.
So when are they going to have us sign up for our fall classes?
Do what now?
When are they going to have us sign up for our classes for next semester?
Good question.
I've signed up for summer classes already. I don't think registration's open for fall at all until the summertime.
Yeah, I don't even know what I'm teaching in the fall, which is kind of unusual, but my dean told us at one of the meetings that we should have that this week to work on, and I haven't seen it yet, so I don't know what they're doing. I'm kind of just like, I'm like y'all, basically. It's kind of like, I don't know what's going to happen.
All up
This is
there.
crazy. Yeah. Yeah. All right. So I'm trying my iPad out today, so we'll see how it goes. I can actually write on the iPad a lot easier than using that crazy mouse. So hopefully that'll help. I do have your test ready to go. I did send you some information about like where you'll upload it and so forth, all of your work. Trying to think what else. Oh, I uploaded the quiz that's been completed now for quiz 4. So that's up there for you. And
The new quiz or the one that we did? The one that we did, right?
the one that y'all did, yeah.
Oh, okay. Sorry. I was like, another quiz? That's sorry. I misheard you. I'm
gosh,
sorry.
no. Oh, gosh, no. Let me close my door real quick.
I have some lawnmowers outside. Is that distracting?
Oh, sure.
No,
Me too.
Okay.
No, we're good.
Yeah, they're building next to my house. Sounds like a giant woodpecker lives next to me.
Oh gosh.
Well, usually I'll have dogs barking, and I'm down to
Running
one
around.
child this morning, so
I live with
crazy.
13 other
Okay.
people in my house, but thankfully it's quiet and I can be here.
That's good. Yeah, right. We pawned one off on my mother-in-law, and she's like, "Oh, okay, great." So I'm sure she's slave labor. Oh well, she needs to work a little bit. Okay, so I did put the notes up on. Let me get mine up here for you. Okay, so I did put my notes up there on Canvas for you. This is the last section of piece of information anyway for our test. Remember the test, even though it says it's scheduled for Tuesday, I think gosh, I need to go back and look, I guess. I've scheduled it for 3 days though. So, yeah, maybe I'll pop out and look at that right before we leave. Okay. That would be
Where's
good.
the test gonna be again? Is it gonna be through Connect Math, or how is that
It's-
gonna go?
What I did was I went ahead and I typed in your questions this time, which I'll never do again, into Canvas. And so you'll go to Canvas, assignments, and the test. It looks like it has like a little rocket ship in a way icon by it. It'll be very obvious that that's what you're to take. But when we're done, I'll pop over there to. I'll see if I can get it up here. I should be able to get it up here. We'll see. But if not, we can move over to Canvas and look at what that test looks like. I mean, just the
Okay,
icon. You can't open it yet.
After we meet
Do what
that
now?
Tuesday, then we can start on it. Is that right? Or are we not going to meet that Tuesday?
We can totally meet that Tuesday. That's fine. I didn't even. I guess when I was scheduling the meetings, I was looking at when test days were, and I was like, oh, well, we don't need to meet that day because we're having a test. And then I was like, oh, wait, they're not necessarily going to be taking the test right then. So those of you who want to come to a meeting on Tuesday, that's fine. I'll be here. Yeah. If it's not, I'll check my schedule. And if it's not on the schedule still, then I'll go back and put it back on. I can't remember if I put it back on yet or not. So. Okay. And Levi, I did get your message. I just haven't had a chance yet to go and take care of that for you.
No worries.
Okay.
No worries.
Okay. But not a problem. I can work with that on my end. Okay. So there's a lot of arithmetic in this area, and I don't want you to get overwhelmed by it. Again, I'm serving two purposes. Yes, I want you to learn the material, of course, well enough to get through it. And then I've got to also make sure that my people are going ahead of us are going to be able to look back on this and at least kind of refresh their memory. So this is called analyzing graphs and functions. And then there's a second piece, which is called a piecewise defined function. They're very simple. You just kind of have to, go with the flow with me as we go through this. First three up here are asking you what type of symmetry would your graph have? Nobody's going to stop you from graphing them on your calculator, okay? So if you want to look at your calculator and for Y1, go in there and type in x to the third just to see what that graph looks like. You're more than welcome to. Nobody's going to stop you, okay? The ones where if we cannot graph them, sometimes it'll say x is equal to, and I'll have a y involved in the problem. And those are the ones that the graphing calculator doesn't help us on. Okay, so I don't plan on giving you one like that on a test. Okay, just FYI, if it doesn't say y equal to, then the calculator is not going to be a lot of good for you. Okay. Up there at the very top, you'll see, let me see if I can get my pen to come on here. Okay. You'll see right here, we have three types of symmetry. We have symmetry with respect to the y-axis, symmetry with respect to the x-axis, and symmetry with respect to the origin, okay? Over here on the side, what you'll see is this is how we actually algebraically figure out which one of these symmetries we have. And for an example, for number one, I've written it out there, how we would attempt this. Let me just explain to you what the heck symmetry means anyway. When you were little, you were asked to cut out a heart for Valentine's Day. And the way we were told to do it is they gave us a piece of construction paper, we would fold it in half, and then we would cut, but the cut we made would only be half of the heart, right?
Right.
Okay, so when you unfolded the paper, it should look like a full heart because there was a crease down the middle of it and both sides of that crease look identical to each other. That's what we mean by symmetry, okay? So if you take that heart, for example, and you talk about the y-axis. I don't want that guy. Hold up. Hello. No. Sorry. Just junk off of here. Thank you, thank you, thank you. All right. When you talk about y-axis symmetry, you're talking about having the y-axis right there. It's gonna be a bad looking Y. And what we're talking about is that whatever's happening to the graph on this side should be happening on the graph on the other side of the y-axis, okay? They should fold down the y-axis. That's what it means to be symmetric to it. So one of our examples, like I've kind of tried to draw here, is the parabola. If the parabola's vertex, where it changes its direction, is down on the origin, and it either goes up or goes down, it's going to be symmetric to the y. The mathematics that goes behind it says, well, if you're symmetric to the y, right here, it says the negative x and a positive x should give you the exact same value. And sure enough, check it out. If you and I were to come right here on this graph and put a point, and then however far over that was, let's pretend that was 2. If I go over here to -2, for example, and try to put a point again, there we go, then those two guys are at the same height. That's what it means to be symmetric to the y. If you go 2 to the right of the origin and 2 to the left of the origin, then if your graph is truly symmetric, both of those points should be attached to the graph at the same height. See how this height would be exactly the same right here?
Mm-hmm.
So if you take a look at the mathematics that I did down here, for y equals x cubed, okay? First of all, when you look at it on your graphing calculator, you can tell that sucker is not going to be symmetric to the y-axis. There's no way, okay? But algebraically, what we do is we say, okay, if this dude really is symmetric to the y-axis, what I'll do is I'll do this substituting test for myself. I'll plug in a negative x where the old x used to be, okay? I'll work it out. It says y equals negative x cubed now. Our test will be, is this the same exact equation as what you started with? Does it look like it's the same?
Oh.
No.
No, because right here, whenever you cube the negative, right? When we cube that negative, well, the negative stays with us. Well, that is not the same as this function right there. It's not the same. So it's not y-axis symmetric, okay? So we move to the next type of symmetry, and the next type of symmetry is the x-axis symmetry. You won't hear people talk about this one very much because if you look at what happens when you talk about the x-axis symmetry, okay, there's our x-axis. And if you have a point, it says the y's will now be opposite from each other. So if I go up to the number, let's say up to, and I go down to down here, if my graph happens to pass through those 2 points, okay, I would say that, yep, sure enough, it looks like it's x-axis symmetric. This time you're folding the top part of the graph across the x-axis to the bottom part of the graph. Do you see how it would fit?
Yeah, I see it.
Okay, so if it folds across the x-axis perfectly, okay, meaning it fits, then we would say we do have x-axis symmetry. Now, the reason why a lot of times we don't see this happen very often is because look at the picture. Is that a function?
No.
No, it's not a function, okay? So for sure, if my graph ever has x-axis symmetry, I know it's not a function because somebody tried to use an x and they got 2 different y's, okay? So try look down here at the arithmetic that I did, okay? For the x-axis, he says, let's plug in negative y. For the old y, the x doesn't change. All right, well, negative x I put in parentheses just so you knew it was my substitution. Well, I ended up with negative y equals x cubed. I'm trying to fight for that original equation. So what I did was I came in here and I said, well, let me divide by -1 on both sides. When I do that, yay, I get the y, don't I? But boo, what happened?
Not the original.
What happens? It's not the original, yeah, because this x cubed that was looking good for me here at the beginning, the minute I went in there and I divided by -1, dang if it didn't change to a negative x cubed. Well, when I go back and I say, okay, are you the same as the original? No. Well, then I don't have x-axis symmetry. I don't have y-axis symmetry either. So I'm not getting the original problem back, which means the point that I changed to didn't stay on the graph. So our last chance, okay, our last chance is origin symmetry. So origin symmetry, this is the one, this is the picture that you guys, if you just graphed it, when you go to your graphing calculator and put in y is equal to x cubed, it'll kind of look like this. Yours will look a lot better than mine does. But that's what he looks like, doesn't he?
Mm-hmm.
Okay. If you check out a point, let's check out a point right here. This point right here on that graph could definitely have been 1, 1. Okay. Because if you cube a 1, you get a 1. Well, check this out. Isn't there a point that if you were to go through the origin opposite quadrant, wouldn't this be the point -1, -1?
Yeah.
Okay. Well, like I said, if you've got it graphed on your calculator, you can definitely check it. Okay. So here's the deal. The only way that you can ever be symmetric to the origin is, notice here, you do a double substitution. The x will be now changed to -x, and the y will now be changed to -y. So you do both of them at the same time. So for y-axis, we went back and we plugged in -x. For x-axis, we plugged in -y. For origin, we plug in both at the same time. Well, check out what happens. The -y I get, and when you take a -x and you cube it, it's still negative. This time when I divide by -1, they both turn out to be positive, don't they? Now, is this right here, the finished product here, is that the same as the original?
Yes.
Yeah. So what I would say is my graph here happens to have origin symmetry. Okay. He is origin symmetric is what he's telling me.
So basically,
Now, like I said, go ahead.
you should try it with y, try it with x, and if you still haven't figured it out, try it with both being negative. Like,
Mhm.
should you go through all 3 of those with all of these?
Well, my thing is I love the idea of just kind of knowing what a picture should look like. And so that's kind of why I drew these little parabolas up here at the top. Here he comes back. Up here at the top to show the y-axis symmetry, and then to show x-axis symmetry. And then this is what a typical origin symmetric graph would look like. If I have a clue about what I think it is, then that's the one I'm going to test.
Okay.
Okay. Now, here's the deal. It's not a 33% chance, okay? There's actually 4 different things that can happen. You can have y-axis symmetry, you can have x-axis symmetry, you can have origin symmetry, or notice here, you might have none, okay? There might not be any symmetry whatsoever. When we were together last time, we talked about a graph transforming itself, and so like it would scoot to the left and scoot up or something like that. Man, once those transformations come in and they move you left or right, you're going to lose all your symmetry. Okay, every single bit of it's going to be gone. So the other 2 examples I have up here, like I said, to me it's easiest if you just go in there and graph this. Okay. And if you've got your graphing calculator, you can type in there for your y1 x squared plus 5. Okay. And to practice what we did last time, What's the parent function?
X to the X squared.
X squared, right? Good. So if you wanted to compare it to the parent, in y1 you could put in x squared plus 5, and in y2 you could put in the parent if you wanted to. The parent, y equals x squared, is symmetric. It's symmetric to which axis?
Why?
Why?
Exactly. It's symmetric to the y. If you have something that's symmetric to the y-axis and you just scoop that picture up 5 units, that's what this thing said it happened. Is it still symmetric to the y?
Yes.
Yeah, sure enough. Okay. So since I know that it's symmetric to the y-axis, that's the only one I would test. Does that make sense?
Yes.
Kind of.
So that means that y needs to be negative, right?
Actually, whichever axis you're symmetric to, it's the other guy.
Okay, so the x is negative for this one.
Exactly. Because if you plug in a negative x, let me see if I can write it right up here real quick. If you plug in a negative x and you square it, what will happen?
It'll still be negative. Or no, it'll get rid of the negative.
Exactly right. So a negative x times a negative x becomes the old x squared, right? Out here you would have had the rest of the problem plus 5. And so sure enough, this is going to end up looking like the original, isn't it? Okay. So to me, it's easier to go and graph the picture and make the decision on, okay, do I see symmetry? Yes. Which one is it? Okay. So if it's the y-axis, let the x go negative. If it's the x-axis symmetric, let the y go negative. And if it's the origin, both of them go in. Okay. Now, unless you're told, okay, unless you're told to algebraically support, okay, your symmetry decision, then you just have to know what a picture would look like and go from that point of view, okay?
Which is not hard to do, because if you look at it.
No, it's not.
Yeah.
Exactly, right. If you take a look at number 3, what do you think number 3 is telling us? You think it'll be symmetric or not?
Symmetric.
Yeah, it's definitely symmetric. To which one?
The y-axis.
Yeah, the absolute value graph parent has half of his graph on the left-hand side of the y-axis and half of it on the right-hand side of the y-axis. So that's how I know that the parent is already symmetric. So if you scoop this guy up or down, guaranteed he's going to still be symmetric. Try do this in your calculator for me. Try put in y equals absolute value of x. Put the -2 in it.
Okay.
Oh my goodness, I do not even know what that says. Hold up. -2 inside the absolute value. Try that.
Okay.
Because I want you to see what happens. See, if we move you left or right, we're in trouble. Does that graph now fold where the y-axis is? Pretend you're folding that picture at the y-axis. Are both sides going to hit each other now?
No.
There's no way, right? Didn't your graph move to the right too just now?
Yes.
Yeah. Okay. So where he, quote, changed his direction, like he's coming down and then he's going back up, when he was coming down, he still is going down on the right-hand side of the y-axis. So there's no way. There's no way the x-axis, I'm sorry, the y-axis can be your symmetry line. All right, does that make sense?
Yes.
Okay. All right. Like I said, this is a lot of arithmetic to support your decision, okay? If I ask you to do an explanation of why you think it's one of these things, then you could be as simple as, I know that this thing is symmetric to whatever axis, and just talk me through it. It'll come up here in just a second, okay? If you look in the middle here, it talks about even and odd functions. Sometimes this notation is very, very troublesome for people. It doesn't look like anything has changed. And I promise you it has, okay? Here's what I want you to know. I want you to know that if someone asks you if your graph is even, then it automatically had symmetry to the y-axis. That's how you know you have an even function, okay? An even function will fold about the y-axis. So far, up in those 3 examples, we actually had 2 that were even functions. Which 2 are even functions in the first 3 problems? Which 2 are even? Because they folded about the y-axis.
Number
2 and
2.
3.
2 and 3.
Number 2 and number 3, right. Number 2 and number 3 both were symmetric to the y, so they're automatically classified as the even function. Now, if you change to what an odd function looks like, then the odd function had to have origin symmetry. I've got dumb ways to remember stuff. O for odd, O for origin. Okay. Notice which type of symmetry they never matched up with a type of function. Which symmetry did they not speak about in this little area?
X-axis.
You got it. And why is the x-axis symmetry not mentioned here, do you think?
Because it's not
Go
a
back and
function.
look at that picture. Yeah, right here, this picture right here. This guy is not even a function, so there's no way. Okay. So when you're talking about symmetry, you can have x-axis, y-axis, origin, or just not any at all. So there's 4 options. When you talk about what type of function are you, when someone says, are you even or odd, it's not a 50-50, okay? You're either odd because you have origin symmetry, you're even because it's a y-axis symmetry, and if you don't make either one of those, then you're neither. You're not either one of those. Alrighty?
So you can be even, odd, neither,
That's it.
and that's it. Okay.
You've got 3 options, right? So if you look at number 5, 6, and 7, okay, what's unique about 5, 6, and 7, just kind of glance at how they're written. They're all polynomial functions, aren't they?
Yeah.
Remember how our polynomials would have the same letter in them and then their powers would be different?
Mhm.
That's what a polynomial looks like. What's wicked about a polynomial is that the main thing that is changing is that the powers on your variables are changing, okay? So like look at number 5. I wrote out in words that we had already talked about that x to the 4th, his degree is 4, isn't it? That's his power. Negative x squared, his degree is a 2, because that's his power. And 2, believe it or not, has a degree of 0. And the reason he has a degree of 0 is this number right here, this 2, is actually 2x to the 0 power. That's really what's going on there. So when you have a constant, his degree is always 0. What's cool about polynomials is that if you can determine all the degrees for each of the terms and classify them as even or odd, then you can tell what type of function you have. All of ours were what?
Even.
They're all even, yeah. And so
So
since all of our,
So what you're saying is if the degrees are even, that makes it an even function.
exactly. Now, this only works, okay, if it's a polynomial function though, okay? So like up in problem number 1 and 2, both of those are also polynomial, but number 3 is not. You see it has the bars around it, so that's absolute value. So that one you can't use this neat trick on. Okay, so if it's polynomial, we can talk this way to each other. If it's not, we can't. Look at 7 down below it. It only has 2 terms, x to the third and negative x. X to the third's degree is what?
3.
3. And negative x, he doesn't show his power, but it's really what?
1.
It's a 1. See, that x is there, so his power is 1. Where in number 5, the 2 that was there didn't even talk about x. So that's why his power was 0. So because the 2 terms have odd degrees, guess what type of function he is?
Odd.
He's odd. Yeah. Pretty easy, yeah?
Yeah.
Will there be a situation where one term is odd and one term is even?
Yeah, go look at number 6. So this one started off looking pretty good, I thought. You know, it's x to the third, so his degree is 3. You've got a negative x, his degree is 1. But then you had a constant out there. And this constant that's sitting out here, this is really 3x to the 0 power. So look at your degrees then. You had a 3 and a 1, both of them were odd, but then you had a degree of 0 right here. Now you don't have just odd or just even. So look at what type of function you are.
Oh, okay.
Okay. He's a
That makes
mixture.
sense.
Okay.
So if you have just like the 3 alone, so it's always a 0 degree if you have a number alone by itself?
Yeah, if you have a number by itself, no variable attached to it, then his degree is automatically 0.
Okay, and you put an x there too?
Well, I do just to show you why it's 0, because we can talk powers and degrees. It's 2 different classifications, so you got to be careful which one you're talking about. We're talking about degrees. So degrees are these things that come in as powers. That's a degree. This guy's not showing his, but there's a variable there. Well, the 3 doesn't even have a variable with it. So it's assumed to have a 0 power.
Okay, cool.
Okay.
Okay.
All right. Now, again, like I said, this only works in polynomial functions. Okay.
Okay.
That's it. It won't work any other time. Cool.
Mm-hmm.
Let's see if he's gonna let me go ahead and pick this next one or not. I don't know if he will. No. Okay. Let me run in here, and I've got to stop this share and then come back in. I do not know why he does this. All right. All right. So this is a lot of times more like what you'll see. You'll see pictures like in 8 and 9 here. And you literally don't know anything about the function, so you can't do that cool routine with the powers like I showed you. So you literally have to think about folding the paper. Okay. Do you agree that if I were to crease the graph here on the y-axis, let me get my pen going again. If you were to crease it right here, do you agree that it would fold on top of itself?
Mm-hmm.
Yeah.
Yeah, it's definitely even. Okay. So that's, to me, if I know that even means y-axis, then I can work my way from there. Okay, so that's the, I guess, the category that you kind of need to hook together. An even function always has y-axis symmetry. Number 9 is a little bit harder to see sometimes. This is actually an odd function. And what I suggest is you just run through there and check some of the points, you know. I found a point that was 1 to the left and 1 up. And so if you have a graph that has a point, let me change colors here real quick. Okay. So if you have a point right here and he's saying I'm negative 1, 1, then the only way you can be an odd function, remember what the algebra said? Change both the x and the y to their opposite. And sure enough, check it out. The x went to a positive and the y went to a negative. So that's an indicator of I think I have an odd function, because whatever point I pick, if the opposite is also on that graph, and I put the little red, I think you can see them, the red points on there. They have to be basically in opposite quadrants from each other. I also picked another point that I could read on there. I picked the point -2, -3. And so I picked this point right here. And so I was like, well, if -2, 3 is on my graph, then it has to have this point on there too. So what's the difference? Well, this tells me go 2 to the right and go 3 down. So if I go 2 to the right and 3 down, there he is. That's how I know I've got an odd function. Another way, if you're a little bit more visual than even this, imagine you and I taking our hands at these two points right here. Let's say we were right here. There we go. And we're right here. And we just turn this thing 180 degrees. With this entire graph, when we turn him 180 degrees, and this part of the graph, would they match? Okay, now it's easier if you're on paper, if you have a piece of paper in front of you, because you can literally like stab the graph at the origin and twist the paper underneath there 180 degrees. You won't know that you have even a different picture. It looks exactly the same. So odd functions also have something called like 180-degree rotation. So that's another way you can tell. Those of you who are coming to pre-cal, we've been talking about our functions in that class lately, and even and odd have come up for us also. So that is something that will travel with you. All right, how do you feel about even and odd, or neither, and symmetry with the X, Y, origin, or not symmetric?
Pretty good.
Put those concepts together for me.
All right.
Okay. Like I said, find one that you can memorize pretty easy. Goofy me, you know, I'm like well, the word odd starts with an O and origin starts with an O. So odd functions have origin symmetry. Okay. Then the only other kind of function you can have is even. Even functions have to now cross across the y-axis. If they cross across the x-axis, that's not a function. So that's not even a player for us when you're talking about functions. This next concept about piecewise defined functions, this is where a lot of people just kind of lose their mind. Please don't, okay? If you'll just listen to me today, I think you'll be just fine, okay? A piecewise defined function tells us that as they were explaining what the graph was going to look like, they had to change their mind midway and draw another piece of function so it actually represented it totally. So in our case here, number 10, you'll notice I have this part right here, and then he switched me to another part right here. Okay. So this one function has two parts. Now you can totally graph this in the calculator. It's just you're going to have a huge mess. When you graph the top part there, that's going to be a full parabola. Look at the graph over here that I put on your paper. This parabola though should only be showing his left side. There is a way to do it on your calculator. It's kind of hard to explain. So I would just say, kind of listen to what I'm doing here. Then all of a sudden he changed to a line, x minus 1, that's a line. And see how he has now a line going up? Okay. All right, so in order for them to describe what was going on, they had to use piecewise defined functions. You and I work with piecewise defined functions every time we go to order food, every time we go to the gas station to pick what kind of gas we want, all that kind of stuff, okay? What it says is like, if you went up there and you said, okay, I want to buy Whataburger Jr., okay? Then across from Whataburger Jr., there's going to be a price, right? There's no wondering what price you should pay because right across from Whataburger Jr., there's a price for you, okay? So this is what it's saying here too. Right here, he asked me at the very beginning, he says, hey, if you use this function f, I'm looking at number 10, and I want you to evaluate, that's a word we've used before, evaluate, what is f of -1? Okay. Well, we've always learned just plug that number in, right?
Mm-hmm.
Okay. Here's the deal though. You can only plug it in one of the pieces, not both. Only one of the pieces. So you'll notice that we have something that looks a little bit odd. We usually don't have this kind of thing here, but notice at the back of this function, these are your restrictions. He says you can use that red piece of function right there if you want to, but here's the condition. You can only use it if your x is less than 0. Is your x less than 0 and f of -1? Okay, thank you, Caroline. Is this value right here less than
Yes.
0? Yeah.
Yes.
Mm-hmm.
-1 is definitely less than 0, isn't it? So that
Mhm.
means that I'm going to take this -1. I'm going to take the first part of the function. I'm going to put in a -1. Maybe not. God love this. Okay. I'm going to put in x for x squared plus 1. I'm going to put in there a -1 squared plus 1. And how much would that be?
2.
It'd be 2. That's how I got the value of 2. I also got the value of 2 by, since they gave me the picture, he said your x is -1. So if I go to -1, that's right here. Okay, that's where that -1 is. If x is -1, where is y? That's what he's asking me. Well, y is up here, isn't he? See that point? How high up did that y go for the red point? He went up 2. Mm-hmm. So he is saying here in this first problem, if x equals -1, y equals what? That's what he's asking you, okay?
Mm-hmm.
So try to look at f of 0. This one here is asking you, which piece of function should you pick if your x is 0?
X -1,
Mm-hmm. Why?
because 0 is greater than or equal to 0.
You got it, right. The number that they're wanting me to evaluate at is 0. So that means my x is a 0. That fits in this bottom category because it says, is your x, which is a 0, bigger than or equal to 0? Yes, it is. So what I would do is I would go in there and I would load in, well, for x, I'd put a 0 -1, and that will give me -1, and that's how I got this answer. Or I could have just gone to the graph, right? Since they gave us a picture. And if you find out where x is 0, that's at the origin. Above that is an open circle. What do open circles mean to us?
You include something, right?
Okay. So open circle versus closed circle. Which one is the include one?
Open
The
one, right?
bracket.
Okay, bracket. Okay. So it's the closed one, right? So this one down here that I put the green mark on, this is the one that's closed up. The one above it is open. If you see an open circle, that does not include the point. It's not inclusive. So if I say I need to know how much am I worth at 0, you can't go up to the open circle because it doesn't give you a value. You have to go down instead to the value that's colored in. And so that's how I know that my answer is -1. Try look at 5. Let's just look at the graph. I did that one in blue, and so I ran all the way out to the number 5 on the x-axis because he says my x is a 5. What's your y? How high up do I have to go to the y?
4.
4. That's why my answer is 4. Now go back to the problem. If x is 5, should you use the red circle piece of my function or the green circle piece of my function?
Red.
Or
Okay.
green.
Is your 5 less than 0?
Oh, I mean, green. Okay. I thought that
There you
was.
go. That's okay. That's okay. And I just realized too, I don't even know if we have colorblind students in my class. So my bad. Should it be the top one or the bottom piece? I guess I should say. So the 5 is what you're evaluating at. That's the x. So if I go back to this blackened box, this is your first decision to make. Do I pick the top one or the bottom one? Well, my x is not less than 0, so I can't pick the top piece. My x is greater than or equal to 0, though, so I can pick the bottom piece. Well, sure enough, if you were to put a 5 in for the x, and you take 1 from it, that gives you 4, doesn't it?
Mm-hmm.
Okay. There's not a lot of math here. It's understanding, okay? But there's not a lot of math to do. Let's go to the number 11. Let's look at it. It has 3 different parts to it. I've done them in purple, green, and orange. So I try to color coordinate everything for you, okay? This first piece right here, I'm not even looking at x squared plus 3 is 7 or 2x minus 1. I'm not going to look at this stuff right here. This is not what I'm looking at. I'm looking at the back. Because at the back here, this is where my first decision has to be made. For the purple, it says h of 1, so that means x is 1. Does it fit in the first, second, or third piece?
First.
Mm-hmm. Because if x is 1, 1 is less than 2, isn't it?
Mm-hmm.
Here, if you try the other ones, 2 is less than or equal to 1, which is less than or equal to 4, no. And then this bottom piece, 1 is bigger than 4, no. It has to be the top piece. So you check this first, okay? That's what you check first. You decide which piece of the function you're going to use, and then now it's important to know, okay? Now it's important for me to know, okay, if I pick this top piece here because my x was less than 2, now I can go load it in. That's how I got 1 squared plus 3 is 4. There's no picture here for me to double check with, but that's okay. The next two, it asks you to find the evaluation of when x is 3 and when x is 4. Well, I'll put both of these in green because if you look at the middle piece here, he says you can only use this function if x is equal to 2 or equal to 4 or any number in between 2 and 4. Is the number 3 between 2 and 4?
Mm-hmm.
Right. When you go to this function, this is a constant piece of function, which means it's always going to be a 7. Your output is always 7, as long as you're equal to 2, bigger than 2, up to 4, or equal to 4. So do you see why both of these pieces, the h of 3 and the h of 4, are both the value of 7?
Mm-hmm.
That's where their x's fit. The last one I did is actually represents the last piece of the function, because check out the x that you're supposed to use. You're supposed to use x is 5. Again, running through this, 5 is not less than 2. 5 is not between 2 and 4. 5 is bigger than 4. So that's why I get to choose this bottom piece right here. Plug the 5 in. I get 2 times 5 minus 1. This is the evaluation right here. That equals to 9. Do not think too deeply about this, okay? You just got to know where to start. When we ask you h of a number, that's x. The first part of the piecewise defined function you go to is the restrictions. This number x will only fit in the top or the middle or the bottom, not all three. Ever. If it ever does, it's not a function, so they've lied to you. So? Probably one of the most missed areas. The advantage you have over what my face-to-face classes would normally have is that you've got a multiple choice test. Now, with multiple choice, do not think for a second I haven't gone in there and thought of ways that people might accidentally do something wrong, okay? So the answer, whoa, hold on just a second. Okay. The answer choices that that I've given you there definitely are possibles if you do it wrong. So be very careful. Let me get to our other page.
These notes are in Canvas, right?
Yes.
I was looking on where the modules were, but I couldn't find it, so.
Well, it's under
chapter 2.
module 2 test. And I think it
Okay,
says what?
check.
Something about recorded notes. And what I'll do too is once this, since we're actually really teaching on this one, I think I also owe you well, no, I think I put that Zoom meeting up there for you. I think I did. I'll put this one up there for you also. Okay, yeah. I'll put this one up there too as soon as I get the link to it. All right, here's another area that's, if you're not real careful, you may make a small mistake, okay? There's no work to be done. We're gonna be looking at pictures, and these pictures are either going to be increasing, which means as you go from left to the right, the picture went up. The picture might decrease, which means from left to right, it went down. And constant, that just means he's flat across, okay? The notation up there in the notes gets very, very difficult for students to read. So I don't have a problem with thinking you know what goes up, what goes down, and what goes flat. So that's what you're thinking about for me. Here's the deal then. When we look at problem number 17, for example, I used 3 different colors here for you because the graph was changing what it was doing. I used the pink part to show that the graph was going up. That's increasing. Then the graph went flat. That's blue. Then the graph went down. That's my green piece. And then the graph decided to go back up. Okay? So does everybody understand the increase, decrease, and constant, the way they look?
Yeah.
Yes.
Okay. All right. So here's the tricky part. Once your eyeball has decided if the graph is going up, down, or flat, your eyeball now needs to go to the x-axis. Okay? So you can definitely, you know, like use the idea that I've got here, like if you make a little mock-up of this graph on your own paper, during the test, especially if you want to use little highlighters for yourself or whatever, like I've done here. But the minute you get done with telling yourself, yes, this is going up, flat, down, and up again, now you've got to tell me, when did it happen? When did it happen? So we're now on the x-axis, okay? And we know at the far left is negative infinity and the far right is positive infinity. Notice the numbers on the number line that I've marked for you. Why do you think it's important that I marked a -2, a 0, and a 2?
So you can see where it's stopping, like
That's right.
it's decreasing.
That's right.
It's constant, and then it was decreasing, now it's increasing.
There you go. Right. So every time it changed the direction it was going, I marked it on the x-axis because that's important to me. Okay. So notice up in the little slots that I had for us up there for increasing. I had 2 increasing pieces. Those were my pinks. Okay. So the first piece, it started off as an increase. Notice it has arrows on both ends of the graph. That's important also. I know that this thing was increasing from negative infinity on the x-axis. Let me get my pen real quick. There we go. I really don't have pink, so we'll go with red. That's close enough. And all the way here, all of this to right there. Would you agree that the graph was going up?
Yes.
Yeah.
So when we say the graph is going up, when did it happen? It happened from negative infinity to -2. That's when it happened. Okay. So that's what we tell people. It's increasing from negative infinity to -2. You're just telling people that you saw the graph go up. That's all you're telling them. You're telling them what x's caused it to go up. We ran into a flat piece, didn't we?
Mm-hmm.
The flat piece started at what?
-2 to 0.
-2 to 0. So right in here, this area, from -2 to 0, the graph was flat. So run up to constant here. And sure enough, for constant, from -2 to 0,
Mm-hmm.
that's what we have. Those are the x values where the graph went flat. Did I tell you where it went flat on the y-axis?
No.
No. See, the y part of the graph has already been done, because when you say you saw something go up, down, or flat, that means you were looking at the y's already. So the y information is over. It's over, okay? Just tell me, when did this happen?
Open liquor bottle, handgun were found in vehicle.
So that's why we're on the x-axis, okay? Then the graph did what?
Oh, then it decreased.
Then it decreased. And the graph went down, and right in between here and here, 0 and 2, that's where the graph went down. So I go to the decreasing part and I write in 0 to 2. And then finally, the graph finishes up by doing what?
Increasing.
He starts to increase again, doesn't he? And so the increase starts at the 2 and goes forever to infinity. Now, we're used to having this little U right here. Remember when we had the little U for like domain and stuff like that?
Yeah.
Mm-hmm.
That's what hooks the 2 little pieces together to let everybody know that there were 2 pieces of increasing. So my only fear of having an online test again is that you don't have this on a piece of paper. You take your paper, you do the best kind of like shorthand job you can of what this thing looks like. Mark it up. It's the easiest way to do it.
And we would use the U, let's say there were 2 points of decreasing or 2 points of constant.
You bet. You bet. Now, one thing I want you to notice, because it doesn't matter if your graph has an arrow or if it has a solid point or if it has an open point at one of the ends, okay? It doesn't matter, because when you increase, decrease, or go constant, you always look at the notation that I've used. What did we use on every single one of these?
Parentheses.
Parentheses. When we talk increase, decrease, constant of any graph, we always use parentheses, okay? Always parentheses. The reason is, think of yourself on a roller coaster. You're going up, 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 up. You get to the very top. You're about to pee your pants anyway because you know what's about to happen, okay? But as you reach that very top, you're not increasing anymore. You haven't started decreasing yet. And so you're still kind of in limbo. So that's why we can't say, hey, I'm at the top, I'm still increasing. No, you're not. Okay, so that's why we use the parentheses. As you start down, you know, between such and such and such and such, that's when you can say, yeah, now I'm decreasing between. Okay, so we don't ever use square brackets, ever, on increase, decrease, and constant. Sometimes we get really wrapped up in how the graph is changing, like wiggling or whatever, and you'll notice on number 18 here, a lot of times people get real excited that like right here and right here, something happened. And so they'll go to their number line on the x-axis and they'll mark it. But remember, the first thing you're supposed to do for me is to decide what is going on in the graph. As you read it from left to right, what's the graph doing?
Decreasing.
He's decreasing, isn't he? Okay. Then when he hit that point, what was he doing to the next point?
Decreasing.
Decreasing. And then from that little like corner to the rest of the graph, what was he doing?
Decreasing.
Decreasing. That sucker decreased the whole time, didn't he? So even though there were like corners where the graph kind of changed at a point, he didn't change his direction ever. He kept going down and down and down. So there's no increasing, so that's why I wrote the word none. There's no flat pieces, so that's why I wrote none. And decreasing, it happened the whole time, didn't it? Make sense?
Yep.
Again, there's not any work, is there?
Oh.
Yeah, I'm not back in the meeting.
Oh, hi, Thomas.
Hey.
Hey,
Sorry.
sorry.
No,
I'm using my cell phone. Yeah, my internet's out, but my cell phone's not. So.
Okay. Okay. Well, I promise I'll put this link up to the Zoom for you, okay?
Thank you. That'd be great.
And it'll have all the markings that I'm marking on it right now. They'll happen. Now, what I noticed was that the audio sometimes gets a little bit ahead of where the writing is, but it'll catch up because I was watching one from earlier today.
Okay.
Down at the bottom of the page there, it kind of starts off talking to you about when these changes happen, like when a graph increases and then changes what it's doing, like it goes constant or it goes decreasing. It's hit what we call a relative max or min point. If you and I are talking about a graph, let's say that the graph was an upside down parabola, okay? Would you agree that this graph is increasing then decreasing if you read it from left to right?
Yes.
Okay. So as it's increasing, that's this piece right here. This is the increasing part of it. He goes up to here, right? And then he starts his decreasing part. Okay. All right, so I've got to increase up to a point, and then he does a decrease on the way out. All right, when that happens, for this particular graph, this is what we call his maximum.
Okay.
But if you ever have a graph like what is printed on your sheet there, see right here, that looks like a maximum, doesn't it? Because he was coming from increase to decrease. That's when a max will happen. But is it the real maximum? Absolutely not, because the real maximum is going to infinity, isn't he? So that's why we use the word relative. Relative to the picture that you see drawn, did it max out, meaning it went from increase to decrease? Or did it hit a minimum, relatively speaking? Because what happens to get to a minimum? What's the graph doing right here?
Going to the lowest
It's
point.
decreasing, and then it changes to what?
Increasing.
That's right. So a decrease, I don't know what letter of alphabet that was. The decrease changed to an increase gives you a minimum. And the increase to a decrease always gives you a maximum. They're relative because they're not the true max and min. So that's why we have to use the word relative in front of it. All right. Again, no work to be done here. Let's go look at how the questions are asked. All right, so we'll give you pictures again. Can't really tell much difference between purple and black, but I promise that's supposed to be purple. If you look at the graph and someone asks you, here's the question, it says, identify and locate any relative maxima, that's just plural for maximum, and minima, that's going to be plural for minimum, just in case you have more than one of a kind. And I left this writing in here because it makes a lot more sense. Everybody's going to be able to see that right down here. Quit moving on me. Right down here without a pen. Here we go. Would you agree that that looks like a relative minimum?
Yes.
Yeah.
All right. That point that I just circled this is at -2, -1. And it says the point -2, -1 is the lowest point in a small interval surrounding x is equal to -2. So when I went to x is -2, I dropped down because I saw a little place where, check out what was happening. He was decreasing, right?
Yes.
And then he started his increase, didn't he? Decrease to increase always gives you a minimum. Read this though. At x is -2, so talking about the point, when x was -2, the function has a relative minimum of. So if someone were to ask you, what's the relative minimum for this graph? Your answer is -1. It's always the y value.
So you don't answer it like in an ordered pair ever?
Right, right.
Okay.
The point is what you and I would locate. And then if they asked us, what is your relative minimum? That means your value. And values are always the y.
Okay.
Likewise, if you go to the point 0, 1, it says, at 0, 1, the increase was happening, and then all of a sudden it changed itself to a decrease. That does look like the highest relative point, doesn't it? And so again, even though you and I would say, well, 0, 1 looks like the, the maximum point. Well, be careful, because what we're saying is that when you went to 0, the function, okay, has a relative maximum of 1. Has a relative maximum of 1. It's the y value. So it makes it easier for us if we identify the point that we're talking about. And then when they ask us relative max or min, we always give them the Y value only. See if 20 makes sense to you. Does it look like this graph has like two bottoms to it in a way?
Mm-hmm. Yes.
Like right here, it looked like it had a bottom, and then like right here, it had a bottom.
Mm-hmm.
And see, when you talk about relative minimums, you're not talking about who was the most minimum. You're talking about when I got to this X value, where was I going from a decrease to an increase? Well, the graph starts decreasing here. He's going down. Then he changed to go up. That's minimum. Here, he went down. He went back up. That's minimum then. So our answers, if someone just asked us, you know, what's your relative minimum? We would say our relative minimum is -2 and our relative minimum is 0. We have 2 of them. The X part of the point is to help you locate the point. It has nothing to do with the value, okay? And then in this graph, it only kind of topped out one time, didn't it?
Mm-hmm.
If you look at the graph right here, it kind of looks like nothing. Here we go. Give me that back. Okay. Right here. And so that point is the 0.23. But again, if we ask you what the relative max or min is, that's the value of 3. Okay. Look at 21.
I'm sorry, I have a question for 20.
Absolutely, go for it.
So it says at x equals -1, the function has a relative minimum of -2. Why is it -1?
Why is it -1?
What the point is.
Yeah. If you go to this point right here, this is the one it's referring to. That point is the point -1.
Oh, okay. I was thinking on the y. I was thinking, shouldn't it be -2 negative? Okay, sorry.
No problem.
Sorry.
No, that's good. No,
Okay.
no. What we did was from the first, number 19, that example, I took out the very first sentence where the point blah, blah is. I just took out that sentence and I went straight to, okay, here's the point of what we're getting to. So that's the reason, because you just didn't see the point.
So basically, we find the points and we just plug them in into whether they're like decreasing or increasing. You know what I'm trying to say? Like
Yes,
whether they're max or the min, yeah.
Right. The increase, decrease, and constant that we just went over definitely fits in with if you have a max or min. Definitely. Okay. Those two concepts go together like symmetry and even and odd go together. When you look at number 21 here, we kind of had a problem like this just a second ago when we were talking about increase, decrease, and constant. What do you notice about number 21?
No arrows.
There's no point.
There's no point, right? Okay. What's the graph doing if you had to talk to me about increase, decrease, and constant? What's this graph doing?
It's all 1.
It's steady, yeah. It's not moving up or down.
Yeah, it didn't change, did it?
Right.
See, increase and decrease, it's obvious when you see that change. Like here's a decrease coming, maybe not. Here's a decrease that would come, and then an increase sends him right back, doesn't he? Okay. This guy here that we're looking at, he no more is doing that than anything. Check it out. Watch the Y values. He's going higher. Get off of here. Ugh. He's getting higher, 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 higher. Yes, he twists, okay, a little bit, but he gets higher, higher, higher. He never changes. So this guy here, we would go back and classify him. Oh, wow. Oh, well. Now I look like I'm really in kindergarten with this. Increasing. all the time, isn't it? So he's increasing here from negative infinity to positive infinity. And so if he doesn't change, wow, that is so ugly.
So that's not a constant in the middle of the graph there? Like,
Constant has to go from one point to another. So it has to have at least a flat to it.
okay.
That is actually not a flat. It kind of looks that way. I understand, but it's not.
Okay.
This is the graph that y'all graphed on your calculator earlier. This is y equals x cubed. Y equals x cubed. And he never sits somewhere and goes flat on you. So if you have a continuous increase or decrease or constant, you'll have no relative max and no relative min, okay? You don't have one. It didn't change directions. So if you don't change your direction, then you're not going to have a max or a min. Now it's important, like on the page right before when we saw that one graph that was decreasing the entire time, if it asks you, is it increasing? And it's not, you have to put none or no or something. Don't leave it blank. Blank means you don't know, okay? So like right here, if we asked you, what's your relative maximum? None, there's not one. What's your relative minimum? None, there's not one. Okay, something to indicate to me that it didn't happen. Okay. So in this section, to me, when I look at it, I kind of look at there's 4 major objectives. The first 2 objectives, though, go together. You talk about symmetry, you can talk about even and odd functions. The last 2 are increase, decrease, and constant, along with then max and mins that are relative to that situation. Learn them in 2 parts, not 4 separated parts. It's easier. Be okay?
Mm-hmm. So yeah.
Oh yeah. You won't know until you get into homework, and I realize that, okay? And so when you get into the homework and, you'll have your notes with you. I don't know if you're starting to now, I just gave up on that video list. I was like, this is ridiculous. Just go to like I wrote you in the announcement, just go to your ebook, pick your chapter, go to that section of the book, and they're all active links then. You don't have to worry about which one should I pick and when. Just go straight to the ebook. The more I fought with trying to change these, somebody sent me something and they didn't set it up as URLs, and it's taking forever to do it. And I was like, this is bull. So just use the ebook.
Yeah, it was better because the homework for tomorrow was pretty hard to do tomorrow, and I had to use the ebook to help out.
Well, and I'll tell you what, I'll move 2.6 and 2.7 homework to Sunday. Will that help?
Yeah, I hope a little bit.
Yes.
I don't want to move it too much further from Sunday because you should be starting to prepare for the test.
Yeah.
Okay. So I'll run in there after this meeting and I'll change those, the due date for 2.6 and 2.7 for you.
Thank you.
Okay, no problem. All right, I know it's a lot to take in. Golly, this is as colorful as I've ever been. Wow. But I will, when I end the meeting, I'll wait for the link to show up and I'll go and post it for you.
Thank you so much.
Okay.
You bet. And I'm so sorry that you have to listen to it again.
No, I want to get back to it because I missed almost all of it.
I didn't know I could draw on here. That's cool.
Yeah, and I've been playing around with my, the one problem I'm having still with the iPad is getting the calculator to show up. And so that's something I'll work on over the weekend, but we'll get it all together. Again, they're not changing anything about when we're coming back. It's still showing April 5th I can't tell you if that's true or not. I have no idea. I'm planning on doing this, and I guess if they decide to bring us back to campus, then that's great. But this is kind of where all my efforts go into right now. Then for you.
Oh,
Thank you so much. We appreciate it, though.
Thank
You
you.
bet.
thank you.
Holler at me
Thank
over the
you.
weekend. Please,
We'll do.
please enjoy some downtime if you can find it. Okay.
Okay.
Have a good day. Thank you, Dr.
All
Hoffman.
right.
Will do.
Y'all stay safe. Okay.
Do.
Thank
Okay.
you.
All right. Bye.
Bye.
You bet.